Alright, hey guys, welcome to Projectile Motion Part 2, kind of just continuing from where we left off last time. So last time we looked at the derivation of the equations of uniformly accelerated motion and how they tend to apply to projectile motion. And in this particular video, we're going to look at working our way through a couple of examples and then just completing a few concept tests. Okay, so the first kind of example that I'm given is a projectile that is launched at some angle with some velocity, and in this case it's a projectile with some initial velocity. Remember, in this case initial velocity we denote by v sub 0 at some angle, right, relative to the horizontal. In this case we are given what the initial velocity is. It is 20 meters per second, and we are given the angle, the release angle, which is 50 degrees to the horizontal. So we are asked to find the range, in other words how far this projectile will ultimately reach. We are asked to find its height above the ground, and we are asked what is the total flight time in the air. Okay, so you might think, well, how the heck, just given this information, would I be able to find that? But remember, we are given some equations of uniformly accelerated motion, so you can write those down. You normally will be provided with them, but the first one looked something like this. Remember, we had some kind of final position is equal to some initial position plus the initial velocity times time plus 1/2 the acceleration times time squared. Remember, with all of these we can subdivide them into their x and y components. The other equation that we have is that we have some final velocity is equal to some initial velocity plus acceleration times time. This can also be divided into x and y components. And we also have a third one, which is the final velocity squared is equal to the initial velocity squared plus 2 times acceleration times the change in distance or displacement. And again, this can be divided into x and y components. So remember, the key concept in the last video was that everything will be treated independently. So you can treat the x and y components completely separately. The only thing that tends to tie all of these together is time, really, and some kind of, it's just time. So we'll leave it at that. So the first thing that we'd want to do is this velocity vector, we'd want to subdivide into its x. So v sub naught x to denote its x component, and its vertical component, which would be v sub naught y. Okay, so remember that v sub naught y is just going to be v sub naught times the sine of the angle, which is going to be this 20 times the sine of 50, which is equal to 15.32, and remember it's in meters per second. This v sub naught x is just v sub naught times the sine, sorry, not the sine, times the cosine of the angle, which is then going to be 20 times the cosine of 50, and that's going to give me 12.86 meters per second. Alright, so where's a good place to start? I normally find that time is a good place to start. Oftentimes that's going to be dependent on the vertical motion, because how long an object spends in the air is going to be subjected to how high you tend to throw that object, right? So which one of these formulas could I use in order to find the time? Well, there's only two that have time in it, and that's equations 1 and 2. The next decision I have to make in terms of which one of the two I will use is dependent on what is the information that I have. Well, if I look at the first one, this change in displacement, if I'm just looking at vertical motion, since the vertical motion is going to tell me how long this object spends in the air, I don't have how high it's going to go, right? I know where it starts. It starts on the ground and it's going to fly through the air and ultimately come down. But this over here is going to tell me its change in vertical displacement. I don't know that yet. I do have its initial vertical velocity though, and I have the acceleration in the vertical direction, but I have two unknowns, so I can't use this one. What about this one? Well, there is something else that I know about projectile motion. I do know what its velocity is at the top. For some instant in time, the velocity at the top, in this case, this would be our initial velocity, vertical velocity here. Our final vertical velocity here will be 0 for some very brief instant in time. I know the acceleration vertically, and time is an unknown. So in this equation I have 3 variables and only 1 unknown, so I would be able to use this one. So let's see what I can do with that. Let me just use a slightly different color here. So if I write this particular equation, this equation number 2, in its y component format, it will tell me that the final velocity in terms of its vertical velocity is going to be equal to the initial vertical velocity plus the acceleration in the y direction times time. Okay, so I want to make time the subject of the formula. So first thing I would do is take this velocity component over to the other side. So it tells me that it's my final y velocity minus my initial y velocity is equal to this acceleration in the y direction times time. And then I'm just going to divide both sides by this acceleration in the y direction. So it's my final velocity in the y direction minus my initial velocity in the y direction divided by my acceleration in the y direction will give me what that time is. So now I can just plug in values that I have. So my final velocity in the y direction we said is going to be 0. My initial velocity in the y direction we said was this 15.32. And my acceleration in the y direction we know is just gravity, so it's minus 9.81. So I'm going to sit with a negative 15.3 divided by negative 9.81, which will give me some positive time value, which is 1.56 seconds. Okay, but the really important aspect about that is just the time from when I launched to when I'm at this highest point. Right, so it's just giving me the time up to that. Does that indicate the final flight time or the complete flight time? No, that's just half of it. So since it's symmetrical up and down, we are ignoring air resistance. So maybe just make a note of that. Ignore the air resistance. So there's no other forces acting on it. It's going to be symmetrical. So since time up is equal to time down, that means that the total time is just going to be equal to time up plus time down. So this is going to be equal to the time it takes to get to the top, and since time up is going to equal how long it takes to come down, it's just literally doubling it up. So it's going to be just 1.56 plus 1.56, which is going to give me 3.12. So that's how long it will take to go all the way up and come all the way back down. Alright, so I could plug that into my answer sheet over here, 3.12 seconds for the total time. Okay, so how high will this object ultimately go? Well, I'd need some equation that can allow me to factor in the change in displacement. So I have two formulas for that. The first one is equation number 1, and the second one is equation number 2. Now that I have calculated time, I can pretty much use either one of these, but I'll pretty much go with, well, let's try it both and see. We should get the same answer, right? I mean, it's gone up to some given height, and regardless of which of these I use, I should get the same answer. So let's just, for educational purposes, try and see which one works out easier. Just got to scoot down a little bit here. Nope, wrong one. Okay, let's see if I can insert some space here. Okay, let's just keep going. So let's try the first one. Well, I'm going to try equation number 3. It seems like the simpler one of the two. Again, we're dealing with vertical motion because I'm trying to find out how high it went vertically. So it'd be my final velocity in the y direction. Let's make that a little bit neater. Final velocity in the y direction squared is equal to my initial velocity in the y direction squared plus 2 times my acceleration in the y direction times this change in distance in the y direction. Alright, so I'm trying to make this displacement in the y direction the subject of the formula, so I would subtract and rearrange. So it's my final velocity squared in the y direction minus my initial velocity in the y direction squared. All of that divided by, oopsie daisy, all of that divided by my acceleration, there we go, finally, 2 times the acceleration in the y direction would give me this change in displacement in the y direction. Nope, that's too much. That's too little. There we go. Okay, so now it's a matter of plugging in the values that I have for this. So my final velocity we said was 0, since I'm looking at the top, squared, minus my initial velocity in the y direction, which was this 15.32 squared, divided by 2 times my acceleration in the y direction, which is this 9.81, and it's a negative, don't forget that, will give me this change in displacement in the y direction, which, once I've plugged in and done all the calculations, gives me 11.96 meters. Okay. Alright, let's try the same thing with equation 1. Remember that over here when I calculated time, this was the time it takes to get to the top, right? This was time up. So, if I rearrange this equation up here slightly, it's basically going to say that my change in displacement in the y direction is equal to my initial velocity in the y direction times time plus 1/2 acceleration in the y direction times time squared. Okay, so it's just a matter of plugging in values again. So it's 15.32 times the time it took to get up, which is 1.56, plus 1/2 of this acceleration in the y direction, which is 9.81 times 1.56 squared. And remember, this 9.81 is a negative value. So a positive times a negative is going to give me a negative. So 1/2 times 9.81, I'm just going to rewrite this one more time. So it's going to be 15.32 times 1.56 will become minus 4.905. Half of 9.81 is 4.905. And like I said, a positive times a negative is this, times this 1.56 squared. So you can see that this velocity value as a function of time is going to decrease by this amount until it gets to the top, right? So once I've plugged all of that in, my final answer, surprise, surprise, becomes 11.96 meters. notice how this is the same as that, right? So you could use either formula. It just depends on what values you are plugging in and how you are breaking this particular example down into its component parts, right? So let's have a quick concept test, and then we at the end of this particular video series. So the first one says, a projectile is fired at some angle theta above the horizontal with an initial speed of v sub naught. What is the x component of the initial velocity vector? Is it a v sub naught cos theta? Is it this should be b? Is it b v sub naught sine theta? Or is it c neither of these? So you should know the answer by now. Try and work your way through it, and we'll go through the answer. Okay, I'm assuming you've given it a go. As we know, it's asking for the horizontal component. The horizontal component that we've just seen is denoted as the velocity in the x direction, and velocity in the x direction is equal to v sub naught times the cosine of theta. It's the adjacent component to this velocity. So in case you've forgotten, the cosine of any angle is equal to the adjacent divided by the hypotenuse, right? So since the hypotenuse in this case is this v sub naught and v sub naught x is the adjacent component, I could rewrite this as the cosine of theta is equal to this v sub naught x. Hypotenuse is v sub naught, and I multiply both sides out. V sub naught cosine of theta is equal to v sub naught x. Okay, so the correct answer therefore is A. Okay, concept test number 3. The acceleration vector of an object is shown. From the graph, what can you say about the x and y components of the acceleration vector? That the ax is negative, ay is positive, ax is positive, ay is negative, ax is positive, ay is positive, ax is negative, ay is negative, or none of these. So try and work your way through it, and we'll go through the answers again. Okay, let's go through the answer in a second. So this acceleration vector is acting straight down, right? Which means that the angle theta is equal to 90 degrees relative to the horizontal, right? If I just had to keep projecting this down, it makes a 90-degree angle with the horizontal. Okay, so what do we know if I had to make this ax, if I had to subdivide this acceleration component into its x and y components? You should know by now that I could write this as a cosine theta, and I could write this as a sine theta. So if I plug in the angle, a cosine of 90 versus a sine of 90, well, the cosine of 90 is equal to 0, and the sine of 90 is equal to 1. Okay, in other words, it's saying that the horizontal component is 0 meters per second squared, and just for instance sake, whatever the value in front of it would be, the sine of 90 is equal to 1 meters per second squared, right? So all of this is being directed downwards, right? Fairly obvious, but the mathematics just reiterates that. So none of this is acting in the horizontal direction. Okay, so our typical convention by this means anything going up is positive and anything going to the right is positive. So in essence, since all of it's acting down, ay is negative, right? So that eliminates a whole bunch. That means that's wrong and that's wrong. Is it A, B, or B, D, or E? What about the x component? Well, we know the x component is 0, so there's none of it's acting in the x direction. So ax negative, nope. Is ax positive? Nope. Is ax negative? Nope. So your answer is E. It's none of the above. Alright. We'll leave it there for now. The next component is going to, or the next video is going to look at projectile motion with changes in the release height. Height of release varies. Everything that we've been looking at so far had projectile motion that starts at some point and ends at some point, but the change in height between release and landing was 0, right? There was no change in the height. What happens when a projectile is released from some height that is higher than the height of landing, or vice versa? What if a projectile is going to land at some height that is higher from which it was released? And that's what we'll look at in the next video. Thanks, guys.